Hello everyone, my name is Elise. I am going to go over with you the glycolysis reaction, chemically, step by step, what happens. Again, remember glycolysis, we are going from a glucose molecule and we are converting that into a 3-carbon molecule, which will later be used in the Krebs cycle and electron transport chain. If it's a eukaryotic cell, if it's a prokaryotic cell, we're just going to use that to go ahead and make energy. So let's go ahead and get started. So we are going to start off this reaction just with the glucose. So I want you to just not look at this right now, and let's start off with glucose. So what is glucose? Glucose is a 6-carbon molecule. It is a sugar, and in order for our cells to function, they use this sugar to convert it into usable energy. So all sorts of cells use this, including the brain, liver, everything needs glucose. So in order for us to keep glucose inside the cell, though, and go through all these different reactions, we will have to chemically change this glucose so that it stays inside the cell and doesn't leave the GLUT receptors. Because, again, glucose can go in or out of the GLUT receptors. So what do we do to make sure that it stays inside the cell? We are going to convert it using an enzyme. So if you notice here at the top, I put and labeled ATP. So what the enzyme will do is we're going to take an ATP molecule, adenine triphosphate, and we're going to steal a phosphate off of there. So we're going to clip that off, and that'll get converted into ADP. That phosphate that we stole from here is going to be added by this enzyme to the end of the glucose molecule at the carbon 6. So we have now converted glucose to a sugar molecule that now has a phosphate here, and that means once this phosphate's added that it can't go back out the GLUT receptor. Okay, it's going to stay inside the cytoplasm of the cell, so where it can be processed chemically through glycolysis for energy. All right, so this is really important. I want you to pay attention up here to something that I wrote. So if it's red, if the arrows are red, that means it's a reversible reaction, meaning that it can go either in the forward direction or the backwards direction in regards to that chemical reaction. However, if it is a black arrow, that means it's a non-reversible reaction, and that means it can only go in the forward direction. So this first step, going from glucose to glucose 6-phosphate, is going to be a irreversible or non-reversible reaction. I actually didn't draw that first initial arrow on here, but I did draw it over here. So notice that it's a black arrow. So we're going from glucose to glucose 6-phosphate, and it's called glucose 6-phosphate because now we have added a phosphate to the 6th carbon of the sugar. Okay, so let's go ahead and take a look at the special enzyme that's going to accomplish that for us. That is called a hexokinase, and inside the liver, that enzyme will actually be what's called a glucokinase that does that for us inside the liver. Everywhere else, it'll be the hexokinase. So step 2, what we're going to do is we're going to take this glucose 6-phosphate and we're going to actually turn it into a different isomer. Now, an isomer means that chemically, if we were to draw out like C6H12O6 with the phosphate, chemically it's going to have that same chemical formula, but now the shape is going to be different. So glucose as a sugar normally has a hexagonal, and I apologize for my drawing, that probably doesn't really look like a great hexagon. But that's going to be a hexagonal shape sugar, glucose. And what we're going to do is we're going to convert it into a different shape, still with 6 carbons overall, same chemical formula, but now it's going to have the shape of a fructose, which is more of like a pentagon or a house shape sugar. Okay, so we're going from this shape to this shape. Okay. Now, again, that's an isomer, and so we're going to have a special enzyme called a phosphohexase isomerase that actually accomplishes that for us. So that's how I memorize this step. Again, we're converting glucose into its isomer, so we're going to use an isomerase. All right, so we go from glucose 6-phosphate, which I labeled as a G6P right here, and we are now going to go from a G6P to a fructose 6-phosphate, which is F6P, what I labeled here. Okay, this is a reversible process, so it can go forwards or backwards. And that'll be important as we talk about gluconeogenesis later on. All right, now the following step, we have now run into another non-reversible reaction. And so this is really important. It can only go in the forward direction. The only way we can overcome this is to actually find loopholes or do other different chemical processes, which again, I'll go over on gluconeogenesis in my next video. But what we're going to do, notice here that we only have one phosphate here, but on this 6-carbon molecule, what do you notice? We've actually added another phosphate to this end. So to do that, again, similar to what we did in the first step, we're going to steal a phosphate from an ATP. This enzyme is going to help do that. And it's going to take that phosphate and add it to the 1 carbon of this fructose molecule. So now we've taken an ATP that's converted to an ADP. We have 2 phosphates. Okay. So you would think this would be called a biphosphate, but that is not true because bi means 2. So you're like, oh yeah, this is a biphosphate. It's actually what's called a bisphosphate. So a bisphosphate means that we have 2 phosphates, but there's actually space in between each phosphate. If this were a biphosphate, the other phosphate would actually be closer here to this 6-carbon. Okay, but because there's space here, it's called a bisphosphate. So we've taken fructose 6-phosphate and we have now converted it into a fructose 1,6-bisphosphate. Okay, and I've labeled that as a F1,6P. Okay, so this is a F1,6P. Or maybe I should label that a BP. Sorry, bisphosphate. There we go. BP. Okay. And that is going to be performed by this phosphofructokinase 1. Because again, we're taking a phosphate. A kinase is a special enzyme that actually either adds or subtracts a phosphate. And so this kinase is adding it to the 1 carbon. So hence why it's called phosphofructokinase 1 or PFK1. So that's a cool hint there too. If you see this -1, you're like, oh, and you see the word kinase, oh, I'm adding or subtracting. Oh, in this case, I'm adding a phosphate to carbon 1. So that's a good way to memorize that step. All right, in step 4, I don't know if you've noticed, maybe you can guess what's happening here. I've actually put this little squiggly here. We are splitting this 6-carbon atom into 2 separate 3-carbon atoms. So we are now splitting it in half, but that's actually going to create 2 separate chemical molecules, 2 separate 3-carbon molecules. So the first one's going to be called a dihydroxyacetone phosphate. And notice that phosphate here that we added earlier is on the 1 carbon for this one. Okay. The next 3-carbon molecule that we're going to create is actually called a glyceraldehyde 3-phosphate. On this carbon, however, the phosphate is actually on the 3rd carbon. So it's, again, a little bit chemically different. So this is going to be performed by the molecule adelase, going from here to here. And now we have gone from, again, the fructose 1,6-bisphosphate to the 2 separate 3-carbon molecules, the dihydroxyacetone phosphate and the glyceraldehyde 3-phosphate. Okay, so important step because now from here on out, we're going to be dealing with 3-carbon molecules instead of a 6-carbon molecule. All right, now notice here that I didn't put like another arrow down. This is more of a forward reaction. It is a reversible reaction. It can be reversed, but in general, what we're going to do is we're going to take this DHAP and it's going to get converted into a GA3P because it actually favors the forward reaction for this one. And the reason why it favors the forward reaction is it's more energetically favorable. So now that we have converted the DHAP into another GA3P, not only do we have 1, but now we have 2 copies of the glyceraldehyde 3-phosphate. Okay, again, this is an isomer of this one, and so it's going to convert it. And so, again, when we're dealing with an isomer, we're going to use an isomerase. Okay, so in this case, we're going to use the triose P isomerase to have this forward reaction occur. Okay, and that'll give us 2 GA3P. And that's important because from here on out, in the next steps, that means that we're always going to have 2 copies of everything. Right, and notice here that in steps 1 through 5, we actually used 2 ATP molecules to make this happen. So steps 1 through 5 are known as the steps that we actually have to use energy. Okay, so we're not gaining energy here, we're using it. So in the next steps, 6 through 10 though, we're actually going to be gaining energy. Okay, 1 through 5, using energy. Steps 6 through 10, we are going to gain it. So I'm going to go ahead and move this up for you guys. So we continue. Let's talk about this. Okay, y'all can see that now. Okay. Alrighty. So now we're on step 6. Okay, so we went here. We're at the GA3P. We have 2 of these. What's going to happen next? So we're actually going to have a very special enzyme here that does a couple of things at this step. So notice I put a NAD plus here. So what's going to happen is this NAD plus, with the help of this enzyme, is going to strip a hydrogen off of here, off of this sugar. And then that's going to create what we call an NADH molecule. Now this is important because NADH are molecules that actually assist with the process of the Krebs cycle and the electron transport chain. Okay, so we're actually going to create not 1, but 2 of these, because remember, every step from here on out is not going to only happen once, but it's going to happen twice. We're going to cycle through twice because we have 2 of these. Okay, so that's one important step. And then also another unique step that you don't see anywhere else here is that this enzyme has the ability to bring in a phosphate from, like, just from the cytoplasm. It's not going to get it from an ATP, so we're not actually losing energy at this step. That phosphate's just going to get added in here. And notice what happens. We actually have 2 phosphates now on this 3-carbon molecule. Here we had 1, we added another. Okay? So again, is there space in between these 2 phosphates? You betcha. So this is not going to be a biphosphate. This is going to be another bisphosphate. So we have now gone from a GA3P molecule, and we've converted that into a 1,3-bis-phosphoglycerate. And again, this is going to happen by a very special enzyme called the GA3P dehydrogenase that allows that to happen. Okay, really cool stuff. All right, so notice what happens. We go from a 2-phosphate 3-carbon molecule. Oh, uh-oh. We're missing one there. So we're actually taking away a phosphate now. We add it just to take it away, right? Crazy. So what are we going to do in this case? We're going to bring back ADP. It only has 2 phosphates. It's going to steal this phosphate here with the help of the enzyme, and it's going to get converted into ATP. But remember, this doesn't only happen once. This is now going to happen twice because everything happens twice. So from this step alone right here, we actually are creating 2 ATP molecules. All right. Again, we took away that phosphate from the 1 carbon, so we no longer have a bisphosphate, right? This is going to get converted into a 1,3-bis-phosphoglycerate now into just a 3-phosphoglycerate. So our 3PG is what I labeled that. Okay. Now, let's go ahead and take a look at the enzyme that's responsible for this lovely taking away of this phosphate. We have a phosphoglycerate kinase. Remember that word kinase, we took away a phosphate. Anytime we're dealing with a kinase, we're dealing with a phosphate group, either adding or subtracting it. Okay, now let's go ahead and take a look at step 8. And step 8, something unique is really going to happen. So we have a phosphate group here, but now look where it actually got moved to. So we're taking the phosphate group and we're taking it from the 3-carbon and we're moving it to the 2-carbon. Now this is not going to be your typical what you call an isomer. This is actually chemically changing this molecule now. And so we have mutated it, and which is why we call this enzyme a mutase that does this. So this is going to be a phosphoglycerate mutase that makes this happen. So now we've gone from a 3-phosphoglycerate to a 2-phosphoglycerate, or a 2PG. Okay? Pretty simple step, nothing too big. Now, again, these next following steps, we're going to really dive into chemically changing this molecule again. Now, it's only a 3-carbon molecule. How much can we chemically change it? Up until this point, up until the 2-phosphoglycerate point, all of the 3-carbon molecules have been structured with single bond carbons. So there's only been a single bond between each carbon. Okay, so it's been structured like this. Only a single bond between each of them. Okay, and then we have this phosphate group up here, right, on that 2 carbon. But now in the next step, we're actually going to convert this 2PG into what we call an enol. And now an enol means that we are going to take these carbons and add a double bond in there. Okay, and then we're also going to add an oxygen group. Usually this would be an OH group, but that hydrogen gets kicked out and that phosphate's going to be there instead. Okay, so a double bonded 3 carbon molecule with an oxygen and a phosphate. Okay, again, that phosphate's still going to be on the 2 carbon molecule, but this is now an enol. It has that double bond. And because it's an enol, that's going to be performed by an enolase or an enolase. Makes sense, right? Enolase. And this is going to now be called, we're going from 2PG to a phosphoenol pyruvate or a PEP. Okay, so this is what we call a PEP. All right. Pretty cool stuff chemically. It's kind of surprising how complex chemically this is. But when you break it down and you draw like this, which I suggest you all do, is, go through each step, draw through it several times and list out everything and try to make those connections. Oh, this is an enol in this step. Oh, enolase. Oh, in this step, we're mutating it, a mutase. In this one, oh, we added or subtracted a kinase. Oh, in this, or a phosphate. So that's a kinase, right? So use those key things in each step to try to help you memorize everything. All right. Just a good tip. Now, last but not least, the last step, step 10, we are going to actually take away this phosphate. Look, there's nothing here on this last one. Taking it away. Oh, and look, there's a black arrow here. So this is our last non-reversible step. Once we go from here to here, that's it. We can't go backwards. All right, so this is a non-reversible reaction, and we're going to take away that phosphate there. And once we do that, that's going to leave us with this 3 carbon molecule that can now be used in the Krebs cycle to continue to make more energy. And how are we going to take away this phosphate here is, again, we're going to ask this enzyme here to bring in an ADP. That ADP is going to steal with the help of that enzyme that phosphate from there, and that's going to make us 2 ATP because, again, this goes through twice. Every single step through 6 through 10 happens twice because we now are using 2 GA3P starting out. Okay, so this is going to net us 2 more ATP, giving us a little bit of energy, and also 2 pyruvate are going to be made from this process. Okay, and that is all the steps of glycolysis. Now, depending on if oxygen is available or not available is what's going to happen next to this pyruvate. Now, in general, glycolysis is an anaerobic reaction, meaning it doesn't need oxygen, but if there is oxygen available, that's what's going to dictate what's going to happen next to this pyruvate. If there's oxygen available, it's going to go to the Krebs cycle through the electron transport chain eventually to make a lot of energy for eukaryotic cells. If it is not available, if there's no oxygen available, it's actually going to go through a fermentation process. In humans, it's usually going to be the lactic acid fermentation process. And I'll go over that a little bit more in my next slides. So the enzyme that performs this last step, making us those 2 pyruvate, is going to be the pyruvate kinase, because again, we took away a phosphate here. Kinases either add or take away phosphate groups. And so we've gone from PEP to pyruvate. All right, thank you. Hope you guys learned a lot.